Today, we will discuss how to replace a switching IC on a PCB with another one and what factors we need to consider during this process. It has a fault that I have partially traced. While I have successfully identified the first fault, the second fault is still undetected. As you can see, I have already removed the switching IC from the PCB. The control voltages associated with it, along with its voltage regulator, specifically the Zener diode, have also been found to be faulty. This Zener diode had its number marked on it, which was 51. I have already removed this diode as part of the repair process. In this video, I will explain how to replace a switching IC on a PCB if the original IC is not available in the market. However, this IC is a slightly different model, and its number is top 264VG, which is currently unavailable in the market. This has caused some challenges for me. I thought, if this situation can happen to me, it might happen to others as well. Therefore, I decided to share with you how you can replace it. The solution is that there are various options you can use as a replacement. For instance, you can make modifications to the SMPS circuit and use a different switching IC or even a completely different device, like a voltage regulator, manufactured by certain companies. However, I currently don't have access to those specific options. On the other hand, I have a wide range of ICs available to me, including those from Power Integration. These ICs belong to the same family and support high voltages, making them suitable for this purpose. In short, I have several options at my disposal that I can use effectively for this replacement. Now you can see that I have created the diagram for top 264VG. You first need to understand this diagram. If you understand these points, we will replace it with another specific IC. Here, you can see that all these are the source pins where the negative of the main supply is connected. The entire process involves connecting this negative to the drain, which is why it is referred to as switching, because one point is being switched with another point. Additionally, this connection is made in series, but it remains incomplete until the required functions in this area are fully executed. This is an important aspect to understand before replacing the IC, as these functionalities ensure the proper operation of the circuit. Now you can see that I have written down the details of all the functions happening in this circuit. Additionally, you can also refer to its datasheet to get precise information. Here's a summary of the key points. V, these are the monitor voltages. X, these represent the current limit. C, these are the control voltages. F, this indicates the frequency. D, this is the drain. S, this is the source. All these elements are utilized in the operation of this IC. Here, we will understand how to achieve the necessary points and adjust the circuit accordingly. The manufacturing company provides detailed guidance in their datasheet on how to properly install the IC and configure the required settings. For example, the monitor voltages have specific limits that are defined in the manual. Currently, the system is receiving 320 volts DC, so we will proceed based on this value. According to the company's recommendations, the DC positive side should have a resistor connected to it. This resistor must be connected directly to the V monitor voltage pin. Doing so will allow you to set the monitor voltages accurately. The company has also provided different formulas for different voltage levels to calculate the appropriate resistance values. However, since our system is running at 320 volts, we can use a 4 megaohms resistor to achieve the required monitor voltage settings. This method ensures that the voltages are configured correctly and the circuit operates as intended. Now, let's talk about the X, current limit, and how it can be set. The company has provided clear instructions on this as well. According to their guidelines, to set the current limit, you need to connect a resistance on the negative side of the 320 volt DC supply. The value of this resistance can be adjusted based on your requirements. The company has also provided a formula to calculate the appropriate resistance value. Once you've determined the correct resistance, you will connect it to the X pin. For a 320 volts DC supply, the maximum resistance value should be set at 12 kilo ohms. If the voltage is lower than 320 volts, then the resistance value will also need to be reduced proportionally. This setup ensures that the current limit is properly configured for your specific application. Now let's talk about the C, control voltages, and where these control voltages come from. This involves a specific logic. When the system is powered on, it generates 320 volts DC. After generating this voltage, the switching IC uses its internal system, which includes a preset timer. Here's how the process works. The timer connects the drain pin directly to the source pin in series for a brief period. This allows the downstream system, such as the chopper, to turn on and start generating the required voltages. However, all of this happens within milliseconds, so it's not noticeable to us, but the process is actively occurring internally. Once the system is on, the next step is to locate the control voltages, which are derived from the chopper circuit. The company has defined limits for these control voltages. The internal voltage regulators of the IC operate within the range of 4.8 volts to 5.8 volts. If the voltage falls below 4.8 volts, the control circuit will not function. To set these control voltages, insert the system into the chopper circuit, which allows different voltages to be generated. 2. You can configure the system to output 12 volts, 15 volts, 8 volts, or any other voltage level required by the system. The control voltage can be adjusted according to the available voltage in the system at that time. Ensuring these control voltages are within the defined range is critical for the proper functioning of the circuit. Now that 15-volt DC is available in the system, a device is connected to it, which is a voltage regulator. 2 types of voltage regulators can be used in this scenario, either a TL431 programmable voltage reference or a Zener diode. In compact systems, TL431 is often preferred. You can use either of these to set up the control voltages properly. Once the 15 volts is set, a Zener diode is added to the system to regulate the voltage further. This Zener diode is rated at 8.2 volts, which means that even if you supply 20 volts or 30 volts, it will only allow 8.2 volts to pass through, blocking anything above that. These 8.2 volts are then fed into the internal voltage regulator, which turns on and stabilizes the system. This ensures that the switching IC becomes stable and the entire system functions properly and efficiently. Now let's talk about frequency, denoted as F, which comes into play at this point. What is F? It refers to frequency, and it is optional. How is it optional? The company explains that if you connect it directly to the source, your system will be set to 132 kHz. However, if you connect it directly to the control point, the system will be set to 66 kHz. You cannot leave this unconnected if it is present in the system. You have the choice to set it to either 132 or 66 kHz, depending on your preference. Now let's discuss the source and drain. For these, the company has installed a P-channel MOSFET. Once the required functions are completed, the gate of the MOSFET is activated according to the current limit. This is because full voltage needs to pass through, and the MOSFET gate fully opens to allow this. As a result, the source and drain are connected in series, and the negative point is routed to the drain. This completes the connection between the negative and positive points. With the connection complete, the chopper is activated, and the system starts functioning seamlessly. Now, let's talk about selecting an alternative IC that can perform the same functions as the original one. Once we understand how the IC operates, the next step is to determine its power rating, how much power it handles, and at what wattage it operates. For example, the first IC is rated for 30 watts. The second IC is rated for 13 watts, which is smaller in capacity and does not have a current limit feature. Similarly, in the case of the top 246, it also lacks a current limit feature. After analyzing these options, the next step is to choose an IC that fits the requirements. In this scenario, I have the option to use ICs from the Y series, such as top 246Y, which is rated for 60 watts, and top 249Y, which is rated for 120 watts. I will use the 60-watt top 246Y because it matches my requirements perfectly. Next, I'll explain how to use it effectively in the circuit. Now, let's take a closer look at the top 246Y IC to understand its features. It contains all the same components as before, C, L, X, S, F, and D, which I've already explained. The only difference lies in the L pin. What is this L? In other ICs, it appears as V or sometimes as M, representing the monitor voltages. However, there's a slight restriction in this IC that needs to be addressed. In the older IC, the maximum resistance value for setting monitor voltages was 4 megaohms, but in this IC, you can only use up to 2 megaohms of resistance. By using a 2 megaohm resistor, the entire system will function properly, and the system will turn on without any issues. This minor adjustment ensures the IC operates as intended. Now that I have selected this IC, I have arranged its pins according to my requirements. Some pins have been bent forward and others backward for proper alignment. The first pin is bent forward, the second pin is bent backward, the third pin is bent forward, and the fourth pin is bent backward. I have also taken an 8-pin base, which is commonly used to fix ICs. I trimmed the pins evenly using a cutter to ensure they fit properly into the base. After doing this, the IC has been successfully installed into the base. Now, with the IC securely fixed in the base, I can easily install it onto the PCB without any issues. Now, the next point I wanted to share with you is about a potential issue within this IC. This problem can occur naturally, but it doesn't happen in every case. However, if it does occur, I will explain how to resolve it. When you check this IC, you might notice that continuity is present across all its points. To investigate further, you need to check the capacitors. When testing capacitors in continuity mode, the capacitors should show continuity briefly and then stop. as they are designed to block DC. If they don't show continuity at all, this is also normal and indicates that the capacitor is functioning correctly. This means that even if continuity isn't displayed, the capacitors may still be fine, as their purpose is to block DC current. It's essential to test them thoroughly to ensure they are not the root cause of any issues in the circuit. Let me explain how this capacitor is showing continuity. Even when I check it outside the system, it appears to be fine. For example, the capacitor C220 installed in the circuit shows continuity. Similarly, diode number 62 also shows continuity, even though there shouldn't be any continuity here. Additionally, the capacitors in the current control system emit a beep indicating continuity. Now the question is, where is the actual problem? After checking all the voltages, it seems likely that either a capacitor is shorted or a diode is shorted, as these components are connected directly to the phase and neutral or positive and negative points in the circuit. Upon further analysis, I found that the IPM has a diode connected to it. When I tested this diode in diode mode, it showed 0 in one direction and 0 in the opposite direction as well. This indicates that the diode is open. Upon closer inspection, it turned out to be a 24-volt Zener diode. To fix this issue, I will 1. Replace the faulty Zener diode with another 24-volt Zener diode. 2. Once the replacement is complete, the system will function properly, and the continuity issue will also be resolved. Now it's time to install the switching IC, and I will explain how to do it. The first step is to set the monitor voltages, which need to be configured to 2 megaohms. Currently, there are 4 megaohm resistors installed in the circuit. I will remove 2 of these resistors and replace them with jumper wires to connect the circuit, achieving the required 2 megaohms. I have already provided a detailed explanation of the IC, so you can identify the pins and attach them accordingly to complete the installation. Following this process ensures the IC is properly configured and ready to function. Now the PCB is fully ready from every aspect, so let me test it and show you what we have done. First, I replaced the diode, and now it shows 0.466 volts during testing. Next, I checked the capacitors in continuity mode, and as you can see, the beeping sound has completely stopped. This indicates that there are no longer any continuity issues with the capacitors. Additionally, the diode displayed a proper value and stopped conducting, which confirms that it is working correctly. This indicates that the system is now functioning properly without any problems. As you can see, I removed the 2 megaohm resistors and replaced them with jumper wires. This adjustment ensures the desired configuration, and you can do the same if needed. Regarding the IC, I made a slight change in the IC number, but the family remains the same. Let me explain why I did this. The previous IC developed an issue as one of its pins, specifically the 4th pin, broke during handling. To proceed, I used a different IC from the same family for testing purposes. Now the unit is operational, the indicator light is on, the switching is functioning correctly, and all the IC wires have been set properly according to the circuit requirements. Click on the left or right thumbnail to watch our next videos, and subscribe. Thank you.